share his screen and start the presentation.
All right, thank you. Thank you, Krishna. Am I getting my screens
Yeah, yeah,
in front
screen
of
is
you?
good.
Yes,
Yeah,
yes. Okay. Let me just change my, so.
yeah, it's good.
Okay, I really have to say, Professor Reddy, thank you so much for organizing this. And I'm Kaimin Shih. I'm the University of Hong Kong. And it's really my great honor and pleasure to be here to share a little bit of the work, among the entire scientific community. And hopefully this will be something that to show you that maybe we can help you some in your future research or anything we can contribute as a part of the collaborations to a lot of audiences. Much better work at this moment, if not also in the future. I really have to say thank you for coming today. Good morning over there in Chicago. I'm currently in Hong Kong, so at this time is the evening time. Is actually also Friday evening time. So it's really at a time that we try to relax ourselves. And more importantly, even before the seminar, I saw some really good old friend like Professor Agni Hotri is over there, and that remind myself the wonderful trip back at the India conference, as what Professor already mentioned. And at the very beginning, Professor Reddy was asking me, can you, give a talk? I was saying that I pretty much tell everything that I know to a lot of my old friends, including in the Indian conference. And then I'm not quite sure whether anything new I can further contribute, but Professor Reddy was saying, well, this may be a better chance to further broadcast the information to more audience. So I say, okay, then please allow me to probably still repeat some of the content that a lot of my old friends already know what I'm doing, and taking this opportunity to kind of present it again. At the same time, hopefully some of the new friends can also be in this very wonderful geoenvironmental group that led by Professor Reddy. Again, I am in the Department of Civil and Environment Engineering field, and I'm not necessarily a real geotechnical person, but I feel really lucky to be included in this geoenvironmental group since the very beginning of my academic career, and particularly with a lot of geo-environmental meetings that you really see a great friend to be together, and a lot of people exchange their different research type and also knowledge, and that's how I am today. So really thank you for this community, gave me so much. So today my topic would be using a technique a lot of people knows about, which is X-ray diffraction technique, to as example to tell people that in fact some of the basic technique that you're using can have a new possibility in your research. So I'll be using 3 examples to look at how the pollutant-mineral interaction can be investigated by X-ray diffraction technique, particularly pushing the X-ray diffraction technique to be more to the quantitative capability. In fact, I was looking at some of the talk before of this wonderful series. I really like a lot of them. I recommend a lot of you, if you have not looked at the previous recording of this seminar series, you should really do that. Among them, I do find some of the previous presenters are presenting some similar content on that. What I'm going to talk about today, which is the quantitative X-ray diffraction technique, which I like them very much. For example, the Professor Maria Chrysakos in the University of Connecticut. She is a wonderful expert in this field as well. And in her talk, in addition to the quantitative X-ray diffraction technique, she was also using the other characterization techniques as part of her talk right there. You should really look at that. And she has been using this quantitative X-ray diffraction technique very wonderfully in a lot of different applications. So I think that's something that made me very comfortable. At least I think I'm in the right community to be with this good scientists. Also, so I remember Professor Susan Burns in the Georgia Tech, in her talk, she was also using this technique to look at the burned clay brick. So I think this really brings us into different kind of possibility, opportunity of using this technique all together to advance our work in the geoenvironmental field. So a little bit about myself. I am in the University of Hong Kong, and I'm basically leading a group so-called environmental material groups. And in our group, we like to work on the pollutant preventions. So that including the prevention by recovery certain resources. At the same time, one of the focal point is look at how to get rid of the pollutants out of our environment metrics. That's probably in so-called the decontamination field. So we can also work on membrane, we can also on catalysts, and we look at the behavior of pollutants above the surface to look at the effect and transport in the environment. But doesn't matter which application that we have been doing so far, we have been always focused on the material, particularly with the surface reaction of the material. And that's what we're real into, and that's what we're relatively spending more time on. And so today I'm going to use 3 examples to introduce some of the work that we have. First one is that let's look at the metal that would be in a sludge or ash. And then how can we make it into new products, or when we try to stabilize it, what are the options that we may have, and how the quantitative X-ray diffraction can help with this. So first of all, again, I'm an environmental engineer, so you probably keep hearing all over the world's environmental engineers are talking about water treatments. Okay, they consider themselves as a water treatment person. They have this magic box of wastewater treatment plants running over there. Actually, even you don't know what this wastewater treatment plant are doing. You must understand its purpose to get the wastewater into this plant, and then you get the clean water out. Most of the environmental engineers, or so-called the water treatment engineer, they only care about how clean I'm treating the water that will be discharged from the wastewater treatment plant. But relatively much less people understand, in fact, we discharge the sludge. And if you look at the pollutant that coming into the wastewater treatment plant, there must be somewhere to go. The pollutant will not disappear by itself. So the cleaner that you're treating your water, the dirtier that the waste sludge they will be end up with. So, and also in that case, in order to treat the water much cleaner, sometimes you have to add more chemicals, invest more of the money and effort, try to get the pollutants out from the wastewater, and then everything end up in more in the waste sludge. This is definitely not sustainable. So what we're trying to do is to see whether this waste sludge will be something that we can make it become useful. And one of the very simple idea is to make it into, say, different kind of construction material, brick, some of them make it into, mix into concrete, whatever. So, okay, if we take a look at the very simple scenario, which is try to make it into brick, we understand we have to get a brick together with its so-called the heavy metal laden sludge mixed together, heat up at a certain temperature. This is a very simple and traditional process in the industry, but its scientific mechanism over there, in fact, is still very complicated and not necessarily fully understood. For example, if you heat the clay into 950 degrees Celsius, you may basically generate 2 types of what we call diffuse spinel type of structure. And both of them are so-called narrow crystalline. You can either have the silica sitting at tetrahedroside, or even have aluminum sitting at tetrahedroside. If you have aluminum sitting at tetrahedroside, in fact, this is what we call the gamma alumina as the material. At the temperature, you may have a chance to react with the heavy metal. So again, a lot of people bring the heavy metal sludge together with the clay and burn it off at relatively high temperature, say about 950, and they find, oh, the heavy metal has been stabilized. But why? That is the question that we try to answer at the very beginning. When we look at the material, that will be further recrystallized. Then we look at one technique that has been invented that was invented for a long time ago. We called it X-ray diffraction. And the X-ray diffraction at the very beginning was you basically have the X-ray shooting your material, and the material go through the crystal structure. And then from the diffraction pattern, you make judges on how the crystal structure is there. And then you know what kind of mineral that you have. So this is a so-called three-dimensional X-ray diffraction single crystal. But a lot of time, particularly in the environmental field, you'll not necessarily get a single crystal material. So what you're getting will be powder. If you get powder, then a lot of lab these days, everyone has it, is what we call X-ray powder diffraction. It's very simple. You have the powder sample to be on the machine, and with the X-ray, instead of a three-dimensional diffraction pattern, you get this so-called diffraction profile right there. Each what we call the peak showed up at different 2 theta becomes your what we call the fingerprints of your material. Okay, one of the very important thing that I like for a technique to develop is the tool and the machine needs to be widely available. And that's exactly what Professor Reddy mentioned. This is quite accessible. A lot of lab can have that. If I'm presenting some technique that's very, very much unreachable, I don't think there's much value over there because it's not really helping people. So I think you have this X-ray diffraction diffractometer for powder, perfect. Then let's get the story rolling. So first of all, as a lot of people understand, remember what I'm trying to say in the thermal treatment process, when the clay going to be transformed into different phases, you may have gamma alumina, but gamma alumina by itself, together with so-called alpha alumina, people so-called corundum, their chemical composition is exactly the same, Al2O3. But on the X-ray diffraction, they're completely different structure. When we have different structure, then we have different X-ray diffraction pattern, and we can use the so-called standard pattern to fit them. For example, if you have an X-ray diffraction pattern right here, profile right here, what you usually go to do is to take the standard pattern, and then you try to fit that. Okay, if all the peak can be expanded by the standard pattern, then you know, for example, in this case, oh, the pattern shows that the sample has phase A, crystal phase A, crystal phase B. That is the perfect use of X-ray diffraction, and that's what a lot of people are trying to do very nicely. But this is what we call the conventional qualitative X-ray diffraction analysis, because you know you have A and B. But if I further ask you a question, how much A there and how much B there, that becomes a relatively difficult question for a lot of people to answer, because they would, you know, I only know A and B because I basically fit that, knowing A is here, B is here, but how much, I don't know. Okay, that would be probably useful for geologists. For example, geologists want to know what kind of mineral phases right there. But for engineers, it's kind of different requirement, if not further advanced. Because for us, we need to know what are the structure right there. The environmental system is complicated. We need to know who are the players right there, and we also need to know how many of each of them, you know, in terms of the quantities of them. Because in the industrial world, I give you a product that's like 5% purity compared to I give you 90% purity. It's completely different products, right? You cannot treat them the same. You cannot treat them with the same value. It's different. So we need to know whether we have done something, but at the same time, we also need to know how much we have done for the reaction that we try to drive into. So that's how we start, by looking at the potential of this technique, by pushing it into more quantitative capability. The key is what we call retrieval refinement analysis. Basically, you take the profile, you take the shape of your peak, and you use the calculation theoretically, and you kind of simulate the peak heights, peak shape, which means the width of the peak, for example, and you try to match it to the standard one. And then you start to know, maybe in terms of quantity, what are the different, the quantity of different crystal phases right there. These days, we won't be really sit down and use hand to calculate it because the actual profile could be very complicated, could be have multiple phases right there. So we use computer simulation to that. So it's in fact pretty much simulating the atomic structure, building atomic structures, the basic model, and you use this basic model to do the combination to try to fit the profile that we observe in your system. And then you know the amounts of different phase represented by different standard profile. So that's how we start. First of all, let's put the heavy metals mixed with kaolinite, molybdenite, gamma, alpha, alumina, even with the iron oxide, and see what are the basic reactions right there. First of all, we find out even gamma alumina, again, gamma alumina and alpha alumina are basically polymorph. They are all AL2O3. But you can see the reaction in reacting with the nickels is different. The behavior is different. At lower temperature, in fact, the gamma alumina was the one that has relatively higher metal incorporation rate. What is the target phase? The target phase is nickel alumina spinel. When it goes to relatively high temperature range, in fact, the alpha alumina is proven to be more capable to capture the nickel becomes stabilized phase, nickel aluminum spinel as well. So this tells you the mineral phase is very important. And in order to know the quantity, really can tell when you are at lower temperature, if your techniques, processing technique will be only capable at lower temperature, then you should choose gamma alumina to be of high efficiency of capture the and transform the heavy metal like nickel. But when you are having a higher temperature capability, then you'll rather use alpha alumina. Similar things that we find out if you have the molybdenite, then you have the kaolinite, for example. Probably at lower temperature, you can use kaolinite as the effective ingredient to capture the heavy metal like nickel. But when you go to relatively high temperature, both molybdenite and kaolinite, in fact, they're acting the same for stabilize your nickel as the target heavy metal. So not only the efficiency of the stabilization is different, the product is also different. For example, if I use gamma alumina to start with, then our product will be of large crystal, very well packed microstructures. But if I'm using the alpha alumina, what I'm actually end up is very porous microstructure. In fact, the nickel alumina spinel in the industry has been considered one type of a catalyst. So if you want to make good use of your material, your product into later on usable catalyst, in fact, you should choose alpha alumina to start with because it naturally give you very nice porous materials at the end. But if you are aiming to stabilize your hazardous metal, then you want this kind of a very dense, large crystal microstructure. So we also try iron, and the news was even more exciting. If you compare to the alumina system, the iron system can pretty much stabilize a nickel probably 200 to 300 degrees Celsius less. That explains a very important scenario is that when you have, let's say, taking the nature clay or soil, try to mix with your heavy metal materials and heavy metal sludge, you burn it out at relatively high temperature. In fact, the iron will actually step out first to stabilize your nickel, stabilize your heavy metal. And once you exhaust the nickel, then they go for alumina at relatively high temperature. So that explains very interestingly the mechanism of why we're using how used to be how people use this material with different composition to start and sometimes have different results. However, I mentioned about rate of refinement analysis, which was, if I remember correctly, the first work was kind of reported in 1970. That was really early. It wasn't it wasn't really popular to be used at the very beginning. One of the reasons is XRD by itself is a very instrument-specific technique, which means if I'm getting you a sample and I'm getting the sample on the instrument, here's my in fact, the profile that you see will be a combination of both sample information and instruments. If you ever had the X-ray diffractometer, you understand there are so many different modules you have to set very carefully together with different filter, together with different sleep. So that instrument effects combination is huge to affect your profile. So every profile is the combination of its two effects, which means if I'm getting the same sample on my machine and on your machine, you will get two different profile. Or I should say, probably the 2 theta peaks is still, position is still right. So qualitatively still right. But if you want to do quantitative calculation, that's not very reliable. So what you have to do instead of conventional pharmacological approach, what you really have to do to make it quantitatively reliable is that you have to do fundamental parameter approach. The way to do fundamental parameter approach is that you have to use your, say, the standard, the LAB6 to really calibrate your machine to the level that you can scream out the instrument effect. So in fact, the sample profile that you have will be reborn into a new profile, and you just refine the new profile. That would make your result carry more what we call the physical meaning of your sample structure. So that's very important. If you cannot do that, then probably a lot of refinement process will involve a lot of errors. So that's first one, fundamental parameter approach. Another thing is a lot of people has been troubled by XRD because the XRD cannot see amorphous. It's very natural because if you don't have a crystal, the XRD cannot see it. And if we look at our nature material, who says that you don't have amorphous content? You might have actually quite a lot of amorphous content right there, and you are taking it for experiment and you only explain your result by the crystallized parts. That's missing too much actually on something that you are not seeing over there. So you have to quantify the amorphous content. So in order to do so, you have to have accurate fundamental parameter approach first, no problem. Second thing is that for the quantification of amorphous content, you gotta have a standard. You gotta have internal standard. And once you know how much internal standard that you have over there, then you do the read or refinement with the known crystalline phases that you found over there. And you go back to calculate, then you understand how much amorphous phases actually right there. If the dosed amount is exactly what you dosed right there, and then it come out exactly the same with your standard, and you understand there's no amorphous content. Usually that's not a case from our experience. So the amorphous content needs to be quantified. So we use this technique to really look at the so-called copper. And it was very interesting. Now we can really quantify at lower temperature because at lower temperature, gamma alumina is amorphous. It's difficult to be quantified. So with the amorphous quantification technique, we now can be able to see how much copper is really incorporated at the relatively low temperature. And we found very interestingly, for let's say this this experiment with copper oxide with alumina, for the alumina experiment, we find it's actually a very interesting window that you have to shoot right there, both for gamma alumina or for alpha alumina. And the window is around 1,000 degrees Celsius. A lot of people consider when we want to stabilize the waste or let it less leachable in the geoenvironment, we burn the temperature as high as possible because we can stabilize much better with much stronger thermal effect. Actually, it's wrong. If you really look at this example, we're telling you there is a window to shoot. That's probably between, I would say 900 or at most, I say 1100. That is the window you have to shoot. You cannot be too low in terms of temperature because you don't have enough incorporation capability. You cannot also be too high temperature because you kind of make it transform to another phase. So this is important, I think, lesson for us to understand. We have to control things at the right range. Otherwise, we will not be able to get the best result out of that. Similar situation also happened in the Caroline system. We also find out very similarly around 1,000 degrees Celsius for incorporating copper. That's the best temperature. You should really pay attention, take advantage of that window. We have done this for a lot of different kind of metal, including zinc as example. We also, again, find out at lower temperature, the gamma alumina is always more powerful for incorporating metal. At higher temperature, in fact, the corundum, which is alpha alumina, is usually more favorable. We try to use all different kind of composition come from the waste stream. For example, the wastewater, the waterworks sludge, mostly enriched by alumina. We do the same thing. We find out the same, the zinc aluminum spinel, that is the phase that stabilize the zinc at a relatively when you're burning this for the new products. And again, there's always a best temperature for you to shoot, not too low, not too high. That is how the also the quantitative analysis can tell us how you control your technique to be just right. And then we have this product we want to test whether it's stabilized. Then what we usually do is to leaching experiment. In addition to the traditional 18-hour TCLP, we have been doing all different kind of leaching experiment. Like this one is, in fact, extend to much longer time because our target was to compare the nickel oxide and nickel spinels. Nickel oxide has been considered very insoluble already. So therefore, for most first 18 hours, even one of first or second days. In fact, you cannot tell the differences of the leachability of the nickel oxide compared to the new nickel spinel phases. But once you extend the leaching period to be longer, you start to see completely different behavior. The spinel phases the spinel phase can stabilize the nickel much, much stronger compared to the nickel oxide by itself. However, one thing we should also pay attention is the leaching behavior, because one of the typical way we look at the dissolution of mineral is congruent dissolution, which means, for example, you have one nickel, two trivalent ion, either alumina in our case or iron in our case. Then if it's completely dissolved in a congruent way, then one nickel coming out, you should have a two trivalent cation coming out together. We find out that's not necessarily the same for all the mineral, because we find out the response of the pH, say in alumina phase or the iron phases, are different. So we start to go through the different concentration of them. And we find out, again, if it's a congruent dissolution, one nickel come out, you should have a two trivalent cation coming out, and the ratio of these divalent and trivalent rate should be 0.5. And that's exactly the same for the nickel aluminum spinel. But for nickel ferrous spinel, I'm serious, it's not the case. The ratio is very, very far off. And what we have to do is to really look at the iron concentration, and we go through what we call the quantum chemistry calculation. What we eventually find out is leaching behavior of nickel aluminum spinel is congruent dissolution. But when it goes to, you use iron to stabilize nickel in the spinel phase, what you will see is a reprecipitation of amorphous iron hydroxides on the surface. This is actually good because you are talking about when the heavy metal to be stabilized, then they're exposed to, say, geoenvironmental environment for leaching process, you actually will have layers of amorphous the iron hydroxide to be covering on the surface to protect your products, prevent the further leaching of nickel. So overall, you can see that it will be successfully using the target mineral phase that you want it to be very efficiently formed to stabilize your hazardous metal nicely, even compared to the silicon oxide. We understand silicon oxide, say in this case for kaolinite sample, even silicon oxide is keep being destroyed and keep leaching out, but the spinel has been still holding on the nickel very, very tightly, maintain a very, very low leachable materials. So overall, we can see similar trend by looking at different mineral phase, identify them, and observing their leaching behavior. You will find a lot of new mineral phase like this one, stabilized by alumina phase, will be much, much more stronger compared to the oxide by itself, either the divalent monovalence of the copper phase. Moreover, you can actually look at a lot of surface behavior. And in this case, we use XPS to look at how the alumina on the surface You can see sometimes alumina will actually be left more on the surface. That means that some of the leaching process will be selectively taking out the maybe take some of the one of the metal right there. So you can actually use that to control how stable of your material that you want to design to be put in the nature environment. So overall, in this lesson, we find out that these days, a lot of people are having the heavy metal containing sludge, for example. They can make it into useful construction material by similar processing to make it ceramic material. They can even use, for example, burning process to be part of the incineration. With that, how much chance we actually can trigger the reaction that we're talking about? Whether we can fine tune the temperature to have more of the beneficial reactions that stabilize the metal much better, in turns also generate more environmentally friendly residues as a bottom ash, for example, if not also bring this bottom ash for making much safer product as part of a resource recovery. I think these are all possible future developments. Probably a lot of you can really help me to finish this important. In the either for environment engineer or geoenvironment engineer, we constantly using adsorbent, right? Either adsorbent as a suspended fashion or column action, try to filter out metals, or even we use clays somehow absorb the metal, or even we make what we call the permeable reactive barrier, try to let the groundwater pass through it, and then you have the metal to be intercepted. Have any of you asked what happened when this metal being absorbed on the particle surface inside the column, in the soil, or even trapped in this barrier? We still have to find a place to deal with them. Remove them from the water is not the end of the story, just like the sludge generation. So the technique that we're trying to investigate, I think provide such thoughts, such possibility for us to establish a more sustainable engineering system, if not also nicely working with meteorology together with the geoenvironment that we have. So that's the case that I kind of start with the sludge with the metal behavior right there, and the purpose is try to stabilize the metal. Let me bring you to another example, but I'll go a little bit quick, a little bit faster because it basically right on the same principle. And this is the recovery of the metallic lead for the cathode ray tube gases. We all understand we have this old-fashioned monitors and nobody really uses this monitor anymore, but a lot less people understand the glass that we use had quite a significant amount of lead because we have to really use that to show the radiation. So the cathode ray CRT gas has been a problem of our environment. Back in old time, they will be collected and making new CRT gas. But since nobody really wants to see this type of monitor anymore, they have no way to be recycled for making new product, and it becomes a waste. If you dispose this waste in the environment, either in a landfill or not even talking about illegal disposal, the lead will later on goes to soil, accumulate, it will be a huge problem. So a lot of people keep thinking, how can we actually stabilize the lead if not also recover that? But one of the fundamental problem in the scientific community is that the glass matrix that capture the lead is a very tight form, which means the lead ions over there is very difficult to be extracted. You pretty much have to just destroy the glass network. And one of the possible way you can think of is to melt, is basically dissolve the entire glass. And you can think of how much silicon oxide you have to, silicon oxide structure you have to kind of destroy and dissolve that. There will be a lot of acid, a lot of chemical they have to use over there. So a lot of people try to use different method to extract the lead, if not also recover it. And a lot of use similar method. But so far, what we actually observed was a lot of method, they are either use relatively high temperature or some of the operations conditions is very critical. This is like maybe vacuums systems and that kind of thing. So it's very expensive to operate and difficult to set up. So what we were thinking is that, okay, what we really want is to have the glass network to react with something in a solid state reaction, if not also actually melt it a little bit. But at the same time, we want to get the lead 2+ ions back to hopefully lead metal. If that's the case, then we can just crush the glasses and we use the mechanical processing, if typical different physical property density, then we can just settle the lead metal. So the key thing is to make the is to reduce the lead into metallic lead. And we thought about one possible way, that is to get zero valent ion, because you have this zero valent ions or basically just ion cuttings, that kind of residues can be used. So we mix this ion powder, zero valent ion powder, together with the CRT funnel glasses, and we find very interesting. Yes, we did it. We reduce the lead in the lead ion in the glass matrix into metallic lead. The evidence right here, we start to see metallic lead coming out. And it has a very interestingly shown out around 600 degrees Celsius, also it's very weak signal, but miraculously, it somehow disappeared at relatively high temperature. So what we try to figure out is that, okay, this comes to the story we're talking about. There is a window we have to shoot. This is not only just a scientific problem, this is also an engineering problem. We have to operate things right. So what we use, again, come back to our quantitative XRD capability, we quantify the metallic lead quantity inside the sample. There's no way for you to use chemistry method to know how much metallic lead you have transformed in the system, because remember, this is not leaching process. This everything is still inside the sample. How much lead right there? You use chemical method, chemical composition, still the same. The lead is still inside there. It doesn't matter whether it's iron form, is in the metallic lead zero form. It's still the same. So you have no way to use chemical method to do such characterizations. XRD is the way to do it. But in order to control this process right, to know how much potentially how much lead you can recover within one type of one runs of operation, then you need to use quantitative the quantitative method. So in this case, we figure out the best concentration, best temperature is around 700 degrees Celsius. Don't use too high temperature or too low, and you also have a certain amount of the lead and iron ratios. You don't want to put too much ratio. This give you probably a little bit more a realistic feeling. Like this 700 degrees Celsius under SEM, you can see the metallic lead coming out very easily. But when you think, okay, let me boost up the temperature a bit higher, maybe I can have a better result, then you were wrong. Because say at 950 degrees Celsius, you actually don't see the metallic lead at all. It kind of dissolve and then go back to the matrix. So again, the tool that we have help us to optimize the operation, tell the engineer what will be the best recipe and process that you should design. So we find out you need to add zero valent ion, but you don't want to add a huge lot of them because it's wasting money, right? So we find out probably, you should add it close to 1, but don't need to be over than 1, or even you add about 0.9. Depends on the temperature you're going to operating. You can just add the iron to be enough instead of too much. Too much iron is not necessarily boost up your performance, just basically waste more iron. Also, the timing. Because it is actually a very dynamic process at different temperature range. So you can probably, in our case, corresponding to different temperature, say 700 degrees Celsius the way we want, 30 minutes, that's enough. You don't want to get it too long because the unwanted process of the lead to be reoxidized into the matrix will occur. So overall, in terms of mechanism, I think this is what we are most interested to find out, that you can have the lead to be reduced and have the metallic lead recover, but you don't want this metallic lead to be further dissolved in the matrix. Overall system needs to be carefully investigated, quantified in order to have a good control of these techniques. So that's another example. Now we have already recovered the metals instead of just like the first example, we just try to stabilize it. Okay, so the first example and second examples are all on metal. You might ask, is XRD is only applicable for metal? My answer is no. It has a lot more potential. And let me use the example to deal with the organics pollutants as an example for you. A lot less people understand or have experiences of working with XRD with organic matters, with organic compounds. So let me do this for you. First of all, we look at one very interesting chemical we call perfluorochemical. It's very in the environmental fields we call persistent organic pollutants. It's quite a new type of research looking at the chemical that is very persistent in the environment. Once you have the organic pollutants that is very persistent, that means it's very long life. It will stay in the environment for a really long time. Even the concentrations are very low, it will keep accumulating, and the healthy impact is really a difficult question to answer. A lot more new findings finding out, a lot more new finding is indicating their problems accumulating in our body, if not also in different environment metrics. This, again, this is type of chemical is a carbon chain with all the hydrogen to be replaced by fluorine and some of the functional group at the ends. So that was one of example. This type of compound, in fact, show up everywhere in your life. It can be on your non-stick pans and carpets, a lot of cortex, the kind of material that repel the water and at the same time and let the air goes in. Even the semiconductor industry has that. Discharge into the industry, and also firefighting foam also have that. So in fact, it's everywhere. And and the chemistry by itself is also quite complicated, but let's just make it simple. In different type of chemicals are basically corresponding different carbon chain length. And in this is you have a sulfonate as a functional group at the end. Same thing if you have carbonic acids as the functional group at the end, corresponding to different chain lengths. At this moment, one of the most commonly found compounds for the sulfonated one is PFOS, and for carboxylase, the functional group is PFOA. So we try to have all this preparation to identify this chemical, but it turned out to be one of the most difficult chemical to deal with or to measure, because you'll be so surprised. A lot of reagent that we use in our say measurements of LC, and even some of the tubing that we use in LC already have this type of chemical as the pollutant. So how can you use a machine that had already full of this type of compounds, and then you still want to measure this compound? So it's very difficult. And one of the things that we use at the time, one of the very early group in the world using this technique is using PFC isolation column. The column is basically try to stop the signal coming from the signal. This is one example. It's coming from the instrument. For example, we have this, even I have a blank sample, complete nothing. The ethanol by itself in the LC, we actually already have this picture showing up. Even use different, we may use some kind of methanol that had relatively lower signal, which means lower background signal, but it's still there. Now we use the brink by use the PFC the isolator columns. We can bring the signal to be a later phase. In that case, this is representing the signal come from the instrument. So when we have the real sample injected, that the real signal will come out at different timing. And in that case, you separate the background signal compared to the signal that you really want to measure. We spent almost 1.5 years time to really make the skill to be good enough to operate. And eventually we take it to measure the wastewater in, see whether they have the PF, this type of a compound. And the answer is bingo. We find it. We find the wastewater has relatively higher PFOS, PFOA as well. And another thing is that we look at the sludge. That was a big surprise. Sludge has been another well concentrated, well PFC concentrated material. In this case, PFOS and PFOAs are there. So this trigger a very interesting concern when we look at so-called the when we look at so-called the waste to resource strategy. A lot of waste to resource strategy could be put us in a very dangerous situation, because if you have this type of compound and in the sludge, and we take the sludge for land application, like a lot of cases in the United States, you might actually make this type of compound go into the food chain. And with that, everything will accumulate into our human body. In fact, a lot of human bodies already have this type of compound. And a lot of people do not know why and how they come from. But if we are not paying attention on this type of scenario, we will end up having a lot of this type of compound going through the sludge, going through the geoenvironment, and then affecting the concentration of this type of compound in our body. So we want to understand the behavior of this type of pollutant in the nature environment. Start look at the absorption behavior of this type of pollutant, and say we find at relatively lower pH, then you have much larger absorption capability of this kind of compound. PFOS is still the one that absorb more. PFOA slightly less. So you should be very, very careful when you are doing the, say, the sludge treatments, or even put in the landfill. You will be having a chance to have them to be in a lower pH range, and then you get the chance for more type of compound to be absorbed on the soil. Also, we look at the different kind of cations may affect the absorption behavior. We find the calciums overall, when you have a higher what we call ion strengths, more ions concentration in the solution, then the absorptions of this type of compound will be much less. That's totally fine. But particularly when you have relatively higher calcium, then absorption will be much less, because the mechanism that we find out is the calcium has this kind of bridging effects of different kind of PFOS, and then keep them from being absorbed. Similar things happen for calcium and magnesium for PFOA. Both of them has this kind of bridging capability. And again, in the geoenvironment, we cannot really get rid of the organics. We have organics that shows their hydrophobic behavior on the particle surface, and how would that actually affect the different absorption behavior of this type of compound. We found out very interestingly, without humic acid compared to a little bit of humic acid, we find the humic acid is in fact will reduce the absorption of this kind of a pollutant, particularly with the different chain lengths. Because when you have the PFOS and PFBUS, which is relatively shorter chains compound, you have the electrostatic capability, and that make these two type of compounds stay on the surface of mineral. If you have the humic acid on the surface, well, you might have the PFOS take a little bit more advantage of this kind of hydrophobic end to be attracted by the humic acid. But in fact, you reduce a lot of electrostatic interaction, and overall the absorption capability will be reduced. This situation will be even more serious for the short chain compound, because they even don't have a chance to take the hydrophobic advantage, because their hydrophobic chains of the compound is relatively short. So this is not something to do with the XRD. It's more looking at the pollutants behavior and fate and transport in the natural environment. But with that, I hope I'm convincing you this type of compound will eventually on the surface of our geomaterials, say sludge. Okay, if you want to control the sludge nicely, not letting being discharged out of the area that you don't want them to be, then use the results and also the finding that we just reported. On the other hand, is that a lot of people will say, okay, if that is a problem, then how about let me use thermal treatments? Because for sludge, it's pretty much two type of process. One is land application, the other one will be thermal treatments. So if I burn it, then there shouldn't be any problem, right? Because it won't be any chance to end up in the food chain anymore. So we find this could be a promising techniques. And when we're talking about the thermal treatment process, we're talking about all different temperature range of a process, from the relatively low temperature drying all the way to very high temperature incinerations, right? However, we find out if you burn this PFCS, perfluorinated compounds, you might eventually end up what we call the perfluorocarbons. This perfluorocarbons is a very greenhouse gas potent pollutants. If we're talking about one part of carbon dioxide is of one parts of the global warming potential, each part of this PFCS, perfluorocarbon, we're talking about several thousand times. So in fact, burning is not a solution yet, because you might reduce the PFCS in the geoenvironment, that's fine, but you are generating another new problem, which is perfluorocarbons. So what we're thinking about, okay, is there any way that we can deal with this situation by manipulating the thermal reactions of the mineral with this type of pollutants? And one of the commonly considered minerals in the sludge conditioning, which could be end up in the incineration process, is calcium hydroxide, for example. So if we have a certain calcium hydroxide in the burning process, what will happen? What are the chemical reaction that actually may reduce the chance of the emission of perfluorocarbons? That's what we're asking ourselves. But in order to look at a thermal treatment process for PFOS, for example, we have to look at whether it will evaporate too early. If it evaporates too early, if the generation of the perfluorocarbons actually have too low temperature, and we don't have a chance to really capture it, or at least sufficiently react with that. So we find out, well, usually you probably will have a temperature go up to 425 degrees Celsius in order to get this perfluorocarbons to be escaped from the system. So we say, okay, then let's try to see whether under this temperature, is there anything really can happen with, or before this temperature has any reaction already possibly triggered, and therefore even at higher temperature, the perfluorocarbons still are not going to be a problem. And what we will be looking at is the ash generated from that. Because from the ash generated, we can do X-ray diffraction, we can do quantitative X-ray diffraction analysis, and we will really see where the fluorine is. Are the fluorine really being released to the air as the fluorocarbons or not? Okay, this is what we find, and this was really, really interesting for us when we first started dealing with this. I think we're kind of the first one in the world dealing the type of this kind of reactions with the PFC. We were very excited. It was actually a little bit more just try it, see what happened. We find out at 350 degrees Celsius, then we find out that fluorine can actually reacting with calcium and form a very famous mineral called calcium fluoride. And again, this happened at 350 degrees Celsius, which was lower than a temperature of 425. What does that mean? That means we will not risking the chance or risking much chance for perfluorocarbon to be generated. Before the generation of perfluorocarbon, we already have the calcium hydroxide to react with the fluorine that stay in the PFCs. Then we stabilize the fluorine instead of letting it goes to air, become the perfluorocarbons. So more interesting things that this reaction happen really fast. If you are talking about, say, 400 degrees Celsius, again, that was even below 425 degrees Celsius, you only need probably at most 5 minutes. Then you can have that reactions to be triggered. If you can afford a little bit high temperature, then in fact, say 600 or even goes up to incineration, 2 minutes will be enough, for overall. But I think when I say 2 minutes enough, means that you can actually reach it at less than 2 minutes. the reaction actually for the calcium fluoride formation is actually really fast. But remember, we're supposed to target a real sludge. We're supposed not to look at simple chemical reactions only. So the sludge is complicated structure. I'm sorry, the chemical compositions and different type of structures of mineral right there. And one of the new surprise that we find out is that in addition to, when we look at real sludge, in addition to calcium fluoride, it may have the chance, because we add a lot of calcium hydroxide. Another chance is that we may have this, what we call the fluoroapatite generated. Fluoroapatite, in fact, is a mineral that, because you have the phosphate right there. And this is actually a very robust mineral apatite. A lot of if you did a lot of soil remediation, you understand a lot of people use apatite, hydroxyl apatite, put on the soil, and that will absorb the heavy metal and generate the apatite phase and prevent the heavy metals to be leached from that phase. It's a very stabilized phase. And in fact, a lot of fluorinated toothpaste, right, or even the fluorinated in the water, is try to get the chance to react with our teeth to have a good fluoroapatite formed over there. So it's actually a very interesting phase, mineral phase, that helping us in a lot of different direction. And we find this in the similar reaction process. So now we have two chances to help us to stabilize the fluorine, prevent them from becoming perfluorocarbons. And now we have to use X-ray diffraction to tell people how to make control of them to generate a reaction that we want. Again, we find out you don't have to put too much calcium, you just only need to put right enough. Generally, probably about 1 part of calcium to 1 part of fluorine can probably have the either at 400 or 600, you should probably have a stabilizer capture rate right there. And as what I'm saying, that if you're using lower temperatures, you probably need about 5 minutes. But if you 5 minutes, but if you use relatively high temperature, less than 2 minutes, you can have the reaction to be achieved. And again, you know, at relatively higher temperatures in general is proportionally to the fixing rates proportionally to be higher when you're using the calcium fluoride mechanisms. Okay, so now let's look at the real sludge. The real sludge, when you have 400 degrees Celsius, 600 degrees Celsius, the overall fluorine fixing rate are pretty much consistent with the calcium fluoride, which means calcium fluoride at 400 degrees Celsius, 600 degrees Celsius, all the mechanism really stabilize the fluorine. Your so-called fluoroapatite is there, but it's not a dominant one. But when it goes to high temperature, say incineration, situation becomes a little bit unexpected, because there's 900 degrees Celsius, the calcium fluoride, when it goes to relatively longer time, the calcium fluoride generation rate is actually going to be decreased, correspondingly to the increase fluoroapatites. That's thermodynamics. So with that, you need to be very careful when you're at very high temperature. You need to know what is dominant phases that helping you do your work. Okay, go back to the optimization process. In fact, if you really can control your temperature around 600 or 700 or even 500 degrees Celsius, it's actually good enough for you to stabilize your fluorine quite nicely to about 80%. And when you go up above 600 degrees Celsius, then your fluorine capability of stabilizing your calcium fluorides reaction pass rate is actually not that efficient anymore, and replaced by the relatively higher efficient stabilizations method route by the fluoroapatites. So again, finally, you can use relatively low temperature, then say 400 degrees Celsius if you're looking for the sludge drying. Then what you would be relying on would be the so-called the calcium fluoride as the mechanism to help you stabilize the fix the fluorine right there. But very interestingly, if you make your calcium, make your temperature to 900 degrees Celsius, and if you have the calcium relatively higher, which means at high temperature like incineration, and you also add a lot of calcium, there is a chance that eventually your fluorine fixing mechanism will be dominated by perfluoroaldehydes. So this gives people a big flexibility of controlling what kind of product they want to end up and what kind of mechanism they want to trigger to make their product to be nicely as what they expected to. So overall, the reaction mechanism was drawn by us. We don't want the type of organic pollutants to become greenhouse gases, potent greenhouse gases. What we've tried to make them into is calcium fluoride or fluoroaldehydes. But at the same time, we cannot overdo, otherwise the calcium fluoride's mechanism later on actually goes to silicon fluoride or even goes to HF. Sometimes, if you carefully at high temperature, you might actually turn this calcium fluoride into the fluoroaldehydes. So that is what the mechanisms behind it and the performance that we see in the quantitative X-ray diffractions. So we work on metal stabilization, we work on metal recovery. The last example that we just shown is on organics. So I hope you to be convinced that it's an interesting tool that we can use for different type of application to help us to build a better geoenvironments. One last minute I just want to spare is other work that we have been using this technique in our Hong Kong EU environmental material groups, including we actually look at how we can recover the phosphates from wastewater, because the precipitation of struvite is a very good resource recovery process. And again, use quantitative X-ray diffraction will help you to know how good of the recover struvite that you're having. We also use this technique to work on a lot of battery materials. It's not necessarily relevant to environment, but I'm just telling you anything that relevant to the minerals at different kind of scale, at different kind of application, X-ray diffractions in a quantitative capability can also help you. We also actually use this technique to look at the high-level radioactive waste civilizations. One of the things that we've been working on is, for example, you look at neodymium at high temperature in a glass ceramic system, how the vacancy of the different cation will be occupied by the surrogates of the nuclear waste atoms. And it's very interesting to see all this kind of metals moving around at different kind of vacancy, which is directly related to the stabilized effects of the product. Lastly, we also can work with biologists. For example, calcium carbonate is usually in the natural form of calcites or aragonite, and a lot of them are the so-called bones of the biomineralization process. And different kind of biology process, when they start from the calcium carbonate, it might be aragonite at a certain environment, certain age to change to calcium calcites. They're all calcium carbonate, so you cannot actually use chemical composition to identify them. You have to look at the mineral phase, which is X-ray diffraction. And in order to quantify at their different stages reaction, then quantitative way is the way that you are going to use. So with the love of X-ray diffractions, nearly 10 years ago, I think we edited the book X-ray diffractions. And then later on in 2016, look at this technique used for all different kind of materials and waste that we want to deal with, that we have the environmental material waste book generated. So again, if you see anything that will be used for, or anything that you thought, hey, that's a new possibility right there, we're here very happy to see whether we're going to help you in whatever we can. Thank you very much. And Professor Radies, or yours, I believe.
Yeah, very good.